Okay, so in this second video we're going to look in more detail at the quantization of angular momentum. So this was shown in the experiment explained in the previous video, the Stern-Gerlach experiment. Here you're measuring the magnetic moment of a group of silver atoms in this case, and what you find is that they split into two groups when you put them through this non-constant magnetic field. Half of them move up in the z direction, half of them move down, and we saw that this was a measure of the z component of their magnetic moment, and we also saw that the z component of the magnetic moment is just proportional to the z component of the angular momentum. Okay, so therefore this experiment provides an alternative way of measuring the angular momentum of these electrons as they move around the atomic nucleus. Okay, so in this video I'm going to explain the general theory of quantization of angular momentum. Okay, angular momentum is actually very special because its quantization is completely independent of the kind of system you're looking at. So when we looked at quantization of energy, we saw that depending upon what the system is, different atoms and so on will have different energy levels. So the values of the energy quantization are very specific to each individual system. Okay, but for angular momentum, the quantization is completely independent of the kind of system you have. Okay, and this has a very deep mathematical reason which I cannot possibly explain in this lecture. But what I am going to do in this lecture is say what the result is. Okay, so what is the quantization of angular momentum that is observed in any kind of system you look at? Okay. Okay, so I'm going to state the results without proof because, as I said, the proof requires quite a lot of mathematical theory. So quantization rules of angular momentum. Okay, so I'm going to give you two rules. The first is for measuring the total angular momentum, the length of the angular momentum vector. So this is usually given by the symbol L squared. So classically you can think about this as the length of the vector squared. Quantum mechanically this is not quite right, and I will explain why later on in the video. Okay, but let's suppose you do an experiment and you measure the total strength of the angular momentum, the length of the vector, like this. Okay, so what you find is that it will take values L squared, which is equal to h divided by 2 pi. So h again is Planck's constant, you see it everywhere in quantum mechanics. H divided by 2 pi squared times a number L times the same number L plus 1. Okay, and this is true where L can be an integer or half an integer, positive. So 0, half, 1, 3 halves, 2, and so on up to infinity. Okay. So again, I can't prove this, but this is the result you find. If you ever measure the total angular momentum squared of a system, then you find it must have a form like this for some integer or half integer L. Okay. Secondly, this is where you are measuring a component of L, so usually we choose the z component, although obviously it doesn't matter, you can choose your axes wherever you like. So here this is a component of L in a particular direction, which is what the Stern-Gerlach experiment does. Okay, and in this case you find the allowed values of Lz are again h over 2 pi times m. Okay, and m again is some number which depends upon L, and in particular its minimum value is minus L, then it goes up in integer units, so minus L plus 1, minus L plus 2, all the way until you hit plus L. Okay. So as an example, if you look at the Stern-Gerlach experiment here, the z component of angular momentum has two possible values. Okay, one is up and one is down. Okay, so this corresponds to the case where L here is a half. Okay, so I'll do two examples. So the first one is the case for these silver atoms. If L is a half, then M can be minus L, which is minus a half, or minus L plus 1, which is a half, which is the same as L, and then you stop. Okay. As a second example, let's suppose that L was equal to 1. So L is equal to 1, so then M minus L is minus 1. Then you add 1 to that to get 0, add 1 to get 1, and here you get to L, you stop. So those are two examples, and this first one, as I said, is the case of iron, a case of silver. Okay, right. So those are the rules. Okay, and like I said, these apply to any system. So no matter what your system looks like, its angular momentum will always be quantized in this way. A little bit of notation now to keep this more simple. You see here both quantization rules have the same constant h over 2 pi, and actually h often comes divided by 2 pi in quantum mechanics. So this is given its own symbol, in fact, because it appears so often. Notation. Okay, so h over 2 pi is given the symbol h with a line going through it. Okay, this is called the reduced Planck's constant. Okay, so often you will see this h bar in quantum mechanical formulas, and this is the first time we've seen it here. Okay, right. So what I want to do in the rest of this video is explain to you why this quantization is so strange, and also how you understand this strangeness in terms of quantum mechanics. Okay, so I want to do this example where L is a half, and I want to suppose that we can imagine that the angular momentum behaves like a vector. Okay, so then what we can do, and we'll take the case where L is a half. Okay, we can do the following experiment. We can use a Stern-Gerlach apparatus to measure Lz. Okay, and let's suppose, just for the sake of argument, we get the case M is a half. So in other words, Lz is h bar divided by 2. Okay, and then after that we can use a different Stern-Gerlach experiment for the same atom. Just send it through another experiment in a different direction to measure the x component of angular momentum. Okay, and again, for the sake of argument, let's suppose we get Lx is also equal to h bar over 2. And then we can send it through a final Stern-Gerlach experiment orientated in the y direction to measure the y component of angular momentum. And let's suppose again we get h bar over 2. Then you might want to write then, okay, so now L is just the vector Lx, Ly, Lz, So this is just h bar over 2 times the vector 1, 1, 1. Okay, so we've determined the angular momentum vector. Okay, and you can even in this case check that L squared gives you 3/4 h bar squared, which is indeed h bar squared times L plus 1, which is what it should be. So that all looks okay, but there are two problems with this, with treating L like a vector in this way. Okay, so I'm going to say two examples of what the problems are. The first one is maybe easiest to understand, right? We've now, if we believe this equation here, we've discovered exactly the direction in which the angular momentum is pointing. Okay, so why don't we just do a Stern-Gerlach experiment oriented in exactly this direction? Okay. Okay, so we can set our vector n to be 1 over square root 3, 1, 1, 1. The factor at the front is just to normalize it to a unit vector. And we use Stern-Gerlach experiment to measure the component of angular momentum in the direction of n. Okay, then clearly the classical explanation is, because L is pointing in exactly this direction, is that we should get the full value of angular momentum, right? So classically we expect L in the direction of n should just be equal to L dot product with the unit vector n, and this clearly is equal to h bar over 2 square root 3 times 3, which is equal to h bar over 2 times the square root of 3. Okay, but if you actually were to do this experiment, so after determining the x, y, and z components of angular momentum, you were to put it through a final apparatus to measure the component of angular momentum in this direction n, then you would not get this result. In fact, what you get is that the angular momentum in this direction n is quantized in exactly the same way as it is in the x, y, and z directions. So when you do this, you will get plus or minus h bar over 2. Okay, so that means that you can't treat L just as a vector like this. Okay, because no matter what direction you measure it, you always just get these two possible answers, plus or minus h bar over 2. Okay, so you cannot determine L as a full vector. Okay, so now I will describe for you a second problem. Okay, and this problem comes from repeated measurements. So let's suppose we do something similar to what we did above. Let's suppose we measure LZ, okay, and then again let's suppose we get h bar over 2, and then we measure LX, okay, and again let's suppose we get h bar over 2. So why don't we just check that our vector is still has the same value in the z component, so we can put it through another Stern-Gerlach experiment to measure Lz again. Okay, and you might expect you will get exactly the same answer, h bar over 2, but you don't. Okay, in fact, what you find is that you get Lz stays the same, h bar over 2, with exactly 50% probability, and the other value with also 50% probability. Okay, so what both of these problems show is that it's impossible to measure all three components of the angular momentum at the same time. Okay, if you try to measure one and then measure another, then that will change the result of the value of the first measurement. So it is impossible to measure all three components, or even two of them, of L. Okay, you can only measure one at a time, and making any one measurement will change the values of measurements in other directions. Okay. So for this reason, it's not really right, or in fact it's not right, to think of angular momentum as just being a vector quantity in quantum mechanics. So instead, how can we think of angular momentum? So in quantum mechanics, angular momentum is not a vector, okay, but it's some kind of function, and again I can't go into details. Okay, and what this function does is tell you the probability that a particular measurement will have a particular value. Okay, so just like in the problem 2 example here, when you measure Lz for the second time, you find 50% chance of plus and 50% chance of minus, and this is what the angular momentum tells you. It doesn't tell you L is pointing like this. It says if you were to measure L in this particular direction, then you have a certain probability to find plus and a certain probability to find minus. It tells you the probability that a certain measurement has a certain value Okay, so symbolically we can write it like this. Angular momentum or general states in quantum mechanics are often written with a notation like this, right? It's not a vector, or at least not a vector in the normal sense. So we write it in a different way, and this is known as bracket notation, which was introduced by Dirac. Don't worry about it. It's just a way of writing angular momentum which shows it's not a classical vector. Okay, and like I said, this function, although I cannot define it exactly, what it tells you is choose a direction you want to measure. So let's suppose I want to measure Lz, and then the function will tell me, okay, if you measure Lz, then you have a 60% chance of having plus, so h bar over 2, and you have a 40% chance of having minus h bar over 2. Okay, and let's suppose that you want to measure Lx. Okay, then you might have a 50-50 chance. And if you want to measure Ly, then let's suppose you have a 20% chance of h bar over 2 and an 80% chance of minus h bar over 2. Okay, so this is what the function tells you. You say, okay, I'm going to do an angular momentum measurement in this direction. And the function will tell you, okay, you have 80% chance of this result, 20% chance of this result. Okay, so that's the first thing. So that is how you define angular momentum in quantum mechanics. It might look strange, but quantum mechanics is very strange the first time you see it. Secondly, this problem 2 shows you something important about this function. Okay, if you measure Lz and then you get plus h over 2, then it should be 100% probability that you get plus h bar over 2, right? Because you've done it, you've measured it. But once you measure Lx and then measure Lz again, you find that the probability has changed just to 50-50. Okay? And the reason for this is in quantum mechanics, every time you make a measurement of a certain quantity, you can change the state of that quantity. So in this case, measuring the Lx component of angular momentum here changes what the function says about measurements in the Ly and Lz directions. Okay, so just need to make a couple of notes and then we can finish. Making a measurement of L in a particular direction changes the values of probabilities of the next measurement okay, and exactly how, again, I cannot define without going into the mathematics. So when you take the Yang-Jia-Yokhat class, you will see the mathematical basis for all of this. And the second note is that just like in problem 1 above, you cannot measure all 3 components with 100% probability. So there is no state L here which will give you 100%, 100%, 100%. Okay? With 100% probabilities for all of Lx, Ly, and Lz. Okay, so if one of these can have 100% probability, but in that case the others cannot. And in fact, in that case, the others must have 50-50% probabilities. Okay, and this is expressed mathematically through something known as an uncertainty relation. Okay, so let me write down the formula for it first, and then I will explain what this formula means. Okay, so this is the formula, and what these symbols are here. So these sigmas denote standard deviation. Okay, and this angular brackets here denote taking the mean or expectation of a quantity, and they are defined as follows. Okay. Suppose that you take a measurement and suppose you have values from a set xi with probabilities given by p of xi, then the let me do mean first. Okay, the mean of the variable x is just defined as the sum over all possible values of that value multiplied by the probability of that value. I mean, I'm guessing you've seen this in a statistics class already, okay? So the mean is defined like this, and the standard deviation in fact, I don't have space there, let me do it underneath. Is defined as the sum over I of the square of the values xi squared minus the mean. Sorry. Okay, I can write it. This is better. Okay, square of the values times the probability minus the mean squared. Okay. So the mean is like the average value of this thing x. So here, this is the average value of LZ. Okay. And in the second case here, the standard deviation tells you how big is the range of values. Okay. So if you're in a state which has 100% h bar over 2 and 0% minus h bar over 2, then this would have a mean just equal to h bar over 2, okay, because it's definitely h bar over 2, and it would have a standard deviation just equal to 0 because there's no uncertainty in the value of LZ. Okay. As a second example, let's suppose I have a 50-50 case. Okay, so in this case you would get that the mean of LZ is going to be 0, right? Because it's just the same probability as being plus as it is being minus, so on average it's 0, and the standard deviation here would be maximum, which would just be equal to h bar over 2. Oh yeah, I should say there's a mistake here. This defines the variance. To define the standard deviation, we need to take the square root of this. Sorry. That was my mistake. So there's a square root here. Okay. Right, okay. So, like I said, I'm hoping you've seen these definitions before in a maths or statistics class. I certainly did at high school, but I don't know about here. Anyway, so now we can go back and try to understand this formula. So what this formula is saying is that the standard deviation, that's the range of possible values for Lx, times the range for Ly, is always greater than or equal to some constant, again Planck's constant is here, times the expectation of Lz. So if we take this first case where LZ is definite, so it's definitely h bar over 2, then here you get h bar over 2 squared on the right hand side, okay, and that tells you that the standard deviation of Lx times standard deviation of Ly must be greater than h bar squared over 4, and this in fact tells you that they must be 50-50, okay? Because this is the largest possible value of standard deviation here, which is exactly equal to h bar over 2. Okay? So you get h bar over 2 times h bar over 2 is greater than or equal to h bar over 2 squared, okay? Which is true because of the equal sign. Okay. So this formula stops you from having a state where you have 100% probabilities for measurements in all three components, Lx, Ly, and Lz. So there must always be some non-zero probability of getting a different value for measurement in a certain direction. Okay. So these two things here are central to the full theory of quantum mechanics. So in quantum mechanics, this is not something that's specific to angular momentum, but actually applies to all measurable quantities. Rather than telling you exactly the values of the quantities, in a general case, you have to talk about probabilities. So the state of the system does not tell you exactly what its energy, position, momentum, and so on is. It will just tell you the probability that a certain measurement will have a certain value, okay, as we've seen here for angular momentum. And secondly, these measurements cannot all be done simultaneously. So if you make a series of measurements, Lx, Ly, and Lz, on the same state, then you cannot have certainty in all three of those measurements in this case here. Okay. And this gives rise to an uncertainty relation. So you may have heard of Heisenberg's uncertainty relation. That's not this one. Heisenberg's uncertainty relation relates to a very similar formula, but when you're measuring the position and momentum of a particle, and that's going to be the content of the fourth video lecture this week. Okay. Right, so that's the end of this video. So I've explained how angular momentum is quantized. I've explained why you can't think of it just like a vector. You have to think of it in terms of these probabilities. And I've also explained why you can't ever measure the three components of angular momentum with 100% accuracy.